Ladies and gentlemen, our dear students, we yet on the first topic of discrete mathematics, and this time round we shall be looking at propositional logic. However, before I start, just a reminder that you take time to look at the introductory video that we recorded for you to be able to understand what discrete math is all about, and also to be able to understand the learning outcomes as they were elaborated in the first module. Now, propositional logic. Why propositional logic? Propositional logic was first pioneered by the famous ancient Greek philosopher called Aristotle. Aristotle was a Greek philosopher between 384 BC and 322 BC. He's the man behind logical reasoning. And what we look in this course, we are able to pick a number of principles that come from this greater philosopher who pioneered the essence of logical reasoning. When we talk about logical reasoning, we're simply talking about the science. We can look, it's not an art per se, but it's the science of how we put our arguments together. Now, logical reasoning or propositional logic for this case, we are looking at the logic inside the computer. That while to a human being, you will be able to make your arguments by combining a number of sentences. For example, combining a number of sentences, applying the feelings about the statements you make. This does not equally apply to the computer. However, we use the computers to manipulate the very same data that human beings have and be able to represent it in the computer systems. So what happens is that as human beings apply feelings to the knowledge they have, the computer on the other side, they use the binary digits of ones and zeros to still be able to represent the same statements. So if, for example, you said it is rainy, I'm feeling happy, the computer cannot represent those feelings, but you can be able to represent such statements using a 1 to mean true or false. In logical propositions, we shall majorly be looking at statements in terms of their falsehoodness or truthfulness. Yeah? Or we can represent what is true with the digit 1, or we represent what is false with a digit 0. So in other words, the computer will only look at the statement in terms of their true, which is a 1, or false, which is a 0. So for example, if you want to look at the statement that it is rainy, then you want to check whether it's actually rainy, and you can confirm that to be a 1, or you can confirm it to be a 0. Before we dive into the details of logic or define what a propositional logic is, we may need to find out, or it will be scratching at the back of our mind, where do we apply propositional logic, or why is it important for you to study propositional logic? Now, among many applications for propositional logic, we have it's applied in computer hardware design. For students who will be computer engineers in terms of the hardware, it will be very important to understand the logic designs. We have what we call the logic gates that send these signals inside the computer. We have system specifications. When you want to make the hard design, the specifications for computer systems, you will need to have this knowledge of propositional logic. We have what we call the Boolean searches. Boolean comes from, the Boolean means it's also the mathematics of 1 and zeros. So when you are making a search of true or false, you'll also apply propositional logic. Then we have logic puzzles. We have representation of real world knowledge into computer knowledge. Yeah. Then in artificial intelligence, actually propositional logic is a very important or critical knowledge for you to acquire when you get into artificial intelligence. In programming, in terms of data structures, computer decision-making points, for example, in algorithm, when you are trying to evaluate next step of decision, you will need to use propositional logic. Then basically in the CPUs, central processing unit. The central processing unit ideally carries out two key actions of logical and arithmetic operations of data. And therefore, propositional logic will also be a very important application. Therefore, as you study this subject, it's important for you to, if you cannot be able to understand better those, but at least it gives you a hint where you are likely to apply propositional logic. So as we start now, this science of computer reasoning, this science of computer decision making, this science that is applied in artificial intelligence, this science that is applied in the CPU operations, we start with key terms. What is a proposition? Because we are talking propositional logic, we need to go look at step by step to appreciate some key concepts. So we have what we call propositions, because logical operations or proposition logic is about proposition. So propositions, we define them as a declarative statement that is either true or false and must have a subject and it has a verb. Now, what we mean is that unlike in our day-to-day life, when I say it is I am happy, yeah, you can evaluate the happiness using feelings. But like I've told you that in the computer, that statement, we only want to represent its truthfulness or falsehoodness. So the computer is not going to look at the feelings of being happy. It will just assign that I am happy, and then maybe you can see the expression on my face and you know that I'm happy. You give it a 1. If, for example, I say I am happy, but I have a gloomy face, then you will put that as a 0. And the computer can be able to represent by alterations of currents or signals inside the computer system to represent as presence of current or absence of current to represent the 1 or 0. So propositional logic is used to study meaning of statements and relationships between them. Because as we talk about a proposition being a declarative statement, it means at a certain point we don't talk about only one statement but many statements. So we have what we call atomic or simple propositional statements. Then we have what we call complex propositional statements, which is a combination of 1 or 2 or more propositions to form the complex statement. I will give examples of a proposition. For example, Kampala is in Uganda. Kampala is in Uganda is an example of a simple proposition. And why is it a proposition? Because it's known fact that Kampala is located in Uganda. Therefore, for that matter, we can know that indeed Kampala is in Uganda. So it's a true statement. Then when we say another example of proposition, 3 plus 5 is equal to 4. That is a false proposition. We give it a false value. Okay? It is a clear fact that when you add 3 plus 5, you get 8. But now because this one we are saying 3 plus 5 is equal to 4 is false because it's a clear known fact. Then we have one where we say he is tall. He is tall is a proposition, but we can't know whether it's true that that person is tall or short. So it is a proposition, but it can have a truth value of 1 or 0. Now, a proposition can't be a question. The reason why we say it is a declaration, it's a declarative statement. When you ask a question, you don't have a position of whether that statement is true or false, okay? Then 2 plus 3 is also not a proposition, okay? Because we can't evaluate its truthfulness and falsehoodness. We can't evaluate its oneness or zeroness, okay? So it's very important for you to know that when you are making when you're talking about a proposition, it is something that is declared, and there must be a way you can assert or try to find whether it is a true or false statement. Okay? Now, I have said that proposition can be grouped into simple or complex proposition. Simple proposition or atomic proposition, it's just a proposition, it's just a single declarative statement that is making an assertion on one entity. So the emphasis here again is that when we are talking about a proposition, we don't care about the details of the meaning. We only care about whether that statement makes truthful or falsehood value, or whether we can assign that statement to be true or false, or whether it can be evaluated in that regard. Okay. You can assign a true propositional statement a value T, meaning true. Or you can assign a false proposition, you can assign it a value F or false. An alternative way, because we know that a computer is a binary system and we use binary language, you can also assign a true proposition number 1, which means true. Or you can assign a false proposition number 0, which also means false. Different logic operation. Now, for you to get compound proposition, there are certain logic operations that are carried out on these propositions, on simple propositions, to get compound propositions. So it's also very important for you as a student to be able to appreciate different logic operations, or what they call the logic connectives that are used to form, that are used to combine simple propositions to form compound propositions. Okay. So truthfulness or falseness of complex proposition shall depend on truth value status of simple. So if you have simple propositions, I've already told you that a simple proposition can either be true or false. I've also told you that if you combine, for you to get a complex proposition, you need to carry out a logic operation on a simple proposition, or on 2 or more simple propositions to get a complex proposition. So what happens is that when you are trying to get the truthfulness of the compound proposition, you still need to use, to get the truthfulness of the compound propositions, you use truth tables to be able to evaluate that truthfulness, okay? But also, the compound proposition truthfulness or falsehoodness, again, will depend on what true values or false values that each of the simple proposition had, okay? Now, how do we represent propositions? One way could be by using a declarative English statement. But also, because we want to carry out these operations mathematically, we assign them what we call small letters that are called propositional variables. For example, you can assign proposition, it is raining, and you assign it P. You can assign proposition that it is shiny, and you assign it Q. You can assign proposition 3 plus 2 is equal to 5. You assign it variable R. So we use those small letters instead of having a full statement, okay? So, for example, if we say Henry eats apples, it can be represented by a propositional variable P, and then also another proposition, Catherine eats chocolates, can be represented by another proposition Q. So whereby you will say P is equal to Henry eats apples, and Q is equal to Catherine eats chocolates. So simple proposition PQ can either be true or false, okay? Now let's go to logical connectives. As I've told you that for you to form complex propositions, you'll need logical connectives. Ideally, we have we have 3 primary logical connectives. Then we derive the other 4 or so are a derivative of those 3 simple. The 3 simple logical connectives are 1, the OR connective, the AND connective, and the NOT connective. Okay? Or some people would say the either or, if you are making a statement that combines 2 simple prepositions using either or, you will say either this or that. Once you have that word of either or to combine 2 statements, then you have it mathematically. We know that that is an OR operation, or is an addition. Now, those are usually represented with the V sign, or you represent it with the plus. Because where you read a statement and it has either or, it simply means that you are making an addition operation. We also have what we call the AND stands for where you say that it's statement A and statement B, the mathematical symbol used for and is either a dot sign or it will be an asterisk or a multiplication sign, okay? Then we have the third simple proposition, logical connective, which is a negation or a not. And the mathematical symbol is a hyphen at the top of a particular letter, or you will use what we call the negation sign. Now, we have other logical connectives, which are derivatives of the original three. Number one, we have the nor, neither nor. If you're using a statement of neither nor, you will have a combination of the or and not, okay? So it means that we'll have again to use the earlier symbols of plus and then negating. Then when you talk about NAND, it's a combination of not and and. And then you have what you call XOR. Now, XOR comes from the OR, the original OR, the first one that we mentioned. But while the OR alone is usually called inclusive OR, the XOR is called exclusive OR, okay? And we shall see what effect it has when two simple propositions are combined. Then the XNOR combines neither nor, but both, okay? And we shall also see how that combination works. Conditional statements. Now, conditional statement, or what we call implication, it's usually used in statements of called the if-then statement. That if proposition A exists, then proposition B, it has an effect on proposition B. Then finally, we have what we call the biconditional statement. These usually take the format of if and only if, and they have a sign of a double-sided arrow, okay? So why is it important for you to be able to appreciate those logical connectives? Because the whole math that we are going to undergo in logical proposition is going to involve combination of those connectives, and it will help us to understand how to argue statements using English statements. I mean, using different logical connectives. How you can make arguments of these statements in English using those logical connectives in word format, and then we shall be able to see mathematically how you represent those statements in the computer system using the propositional variables. So we shall start with the or which we have called the inclusive or. Okay? So we have said that the inclusive or is used for carrying out addition operations on logical statements. So it's majorly where you see the or, either or, and it's only that. It means that that statement you are reading in English can be converted into a plus inside the computer system, okay? So in sentence format, it's represented by either or, but in symbolic form, you will have using a V sign or an addition sign, okay? Now let's take an example. P to be the proposition Henry eats apples, and Q to be the proposition Catherine eats chocolates. As represented here below, P is equal to Henry eats apples, while Q is equal to Catherine eats chocolates. So a simple proposition P and Q can either be true or false. So a logical connective of either or can be used to join two or more propositions to form a compound proposition as follows. So if you have P is equal to Henry eats apples and Catherine eats chocolates, we can use the either or to form an English statement to combine those two. And we can read it as follows in English. Either Henry eats apples or Catherine eats chocolates. So what we realize here is that we had two simple propositions which have now been joined using the word either or. So you can see in that statement that we have used the either or to combine those two simple propositions to form a compound or complex proposition. Now mathematically, we can represent it as P Because remember we said that you can represent simple proposition using propositional variables. And in this case we have propositional variable P and Q. So we can now represent the statement either Henry eats apples or Catherine eats chocolates using variable statement P plus Q. P plus Q, or P disjunction Q, or P disjunction Q as represented there. Now, after you get the complex statement or you get the compound proposition,